All right, so this is my presentation on the Peltier cooler slash thermoelectric heat pump. So you may be wondering why I have two names up there. It's because it's called a lot of different things. There's Peltier cooler, Peltier heater, solid state active heat pump, thermoelectric cooler or TEC. Lot of different names for it. But why did I choose it? Well, first off, it's cool. But all right. But actually, because it is cool, it cools things, also heats things. But cooling is its main purpose. And over the summer, my room was very hot, and I wanted it to be less hot when I was sleeping. So I, toyed around with the idea of using one of these devices to make a self-cooling pillow. I thought would be cool. Never ended up happening, but I did like the idea. So, all right, how does it work? So basically, there is a cold side and a hot side, and heat is transferred from the cold side to the hot side. And it is a semiconductor device, or a solid-state thermal energy pump, and uses N-type and P-type semiconductors to do this. So the working principle behind it is the Peltier effect. So basically, current flows to the junctions of the two semiconductors. Heat is removed at one junction and deposited at the other junction. So as you can see, there is little P and N type dice there. So these are composed of material. So the P-type obviously are composed of material having a deficiency in electrons, while the N-type have an excess of electrons. And when the current flows up and down through the module, it attempts to establish a new equilibrium between the materials. So it treats the P-type material as a hot junction needing to be cooled, and the N-type as a cool junction needing to be heated. But since the material is actually at the same temperature, it just creates a temperature gradient between the two sides. So the direction of current, actually, you can just, if you change from, as you can see, there's a positive and a negative side. But if you put positive current to the negative side, the cold side there will become the hot side, and the hot side will become the cold side. So you can change the direction of it. And you can also very finely tune how much is heated or cooled based off the current going through it. So there is an equation there, Q equals PIT. What does this mean? So this means that the heat absorption, Q, is given by P, the Peltier coefficient, I, current, and just time. That's all it takes. Wow, okay. And these machines, or these devices, are also sort of thermoelectric generators. So they can be used as thermoelectric generators, meaning that if there is a voltage difference across the two sides, a little bit of energy, a little bit of voltage will be created. So thermoelectric generators are a very similar device that work on similar principle, the Seebeck effect, which is just the opposite of the Peltier effect. They're kind of inverse. But they are different because a Peltier cooler will be a very poor thermoelectric generator, and vice versa. All right, so construction. So there are these plates you can see in the bottom left. They are normally ceramic. This is what connects with the outside world. They're normally ceramic, but can sometimes be metallized, as you can see there. And here you get an inner working little visual of the actual semiconductor pairs, or the cube dice things. So they are connected electrically in series and thermally in parallel. So they're all, it just winds through all of it. But whichever side's making hot or cold, it's the same one. So it's not working as should, it's working in parallel. And the way it's worked is, you can see They are connected with just a little thin bit of conductor, normally copper, because it's both thermally and electrically conductive. That gets it nice and series. You can get this grid, works very well. Common materials that are used are bismuth telluride, antimony telluride, and bismuth selenide. This is because it works with both N and P type. It's about the same, and it has good thermal performances from about like 180 to 400 Kelvin. It's a huge range, love it. So the cooling effect of any unit using thermoelectric coolers is proportional to the number of like these coolers or dice used. So it's as you increase area, size, and the number of dice you can fit on them, increases the cooling effect. And typically, multiple thermoelectric coolers are connected side by side and then placed between two metal plates, as you can see. However, they can also be multiple units of these can be stacked on top of each other, one after the other, to create a multiple stage cooler. And this can create a greater difference in heat or heat flux. Because of a single stage thermoelectric cooler can increase a maximum temperature difference from the hot to cold side of about 70-ish degrees Celsius. All right, so applications. To know where they're used, first you need to know why they are used. So the benefits: there are no moving parts. It is a solid state, nothing moves. It's just moving heat back and forth. So this means there is very low maintenance and a very long lifetime. And it's also very controllable. As I said, you change the current a little bit, and that affects how much heat is pumped. So you can get very, very precise temperature control up to like 0.1, or I'm sure even higher, even smaller fractions of degrees. It is small, portable, so you can fit it in a lot of places. And it can deal with extreme environments or remote locations, stuff like that. Drawbacks though. It is a lot less energy efficient than conventional vapor compression refrigeration systems. And also can only have that temperature difference, the heat flux can only be so much. But uses, right? Thermocycler. So that is a particular type of one, and it is used in polymerase chain reactions, or PCR machines. So this is used to amplify DNA and RNA samples. In our current climate, this is incredibly important because that is a common way to do a coronavirus test. Very common is that you see if you can find any the viral RNA in there. That's a test. It's also used in scientific equipment. The temperature control is very important for things like laser rays, or radio telescopes or stuff like that, where change in temperature can create a difference in wavelength, and you want to keep the wavelength very steady. And then also, of course, consumer electronics, portable coolers, camping gear, dehumidifiers, printers, all that sort of stuff. So data sheet and buying guide. All right. So as you can see here, here's just a little bit. So there is going to be an input voltage, an input current, terminal resistance, and I would say the most important is the Q max. And I guess T max, but Q max is probably going to be what you're looking for. Maybe also input voltage and current. But Q max is going to be how much heat it can pump. So you can see below we have two models, the CP 2014 7H, which is about $15. That has a Q of around 4.4 degrees Celsius per watt. And then we have a CP 2034 5H, which is around $25. So that is has a Q max of around 18, and it's $10 more expensive. These are all pretty expensive devices, to be honest. They're all in the tens of dollars range. Right, so here is just a quick side-by-side of the two. You can see this input voltage, which has an input voltage you know, as it cools more, you can see the bottom, as it cools more, it will pull a little bit more current, or it will pull, yeah, a little bit more current, but not too much. It's pretty steady, pretty linear, which is nice. And here we have a different data sheet. The previous one from DigiKey, and this is from TE Technology. As you can see, it's the same sort of things. It has hue, voltage, stuff like that. One of the things that's missing is actually it doesn't have a like theta junction case, which I'm very confused about. I don't know why. I could not find it on any of the data sheets I looked at. But if you look up here at the Walmart.com example, these are often used with these massive heat sinks and fans, because it's moving a lot of heat around, you know, especially on the hot side. You don't want the hot side to get too hot. So you have to move that heat away from it so it can keep cooling the other side. But apparently they don't. So yeah, a little bit confused about that. Everything else makes sense. And here is my references. I have many. Yeah. All right.